We'll start streaming here. Welcome back. So we have some new stuff to talk about today. This is one of my favorite lectures. How many of you have had the chance to teach before? You have? Do you have favorite lectures yet?
Analytic geometry.
What?
Analytic geometry.
Analytic geometry.
Yeah.
Yowza. Okay. That is a real barn burner. Yes, analytic geometry. Yeah.
And differential equations.
And differential equations. Damn.
My bachelor degree was in maths.
Mathematics.
Yeah. Also,
Okay.
my first master's degree was mixture of maths and educational assessment. That's why.
Okay.
More computational stuff.
Okay, good to know. So if you hear me say anything stupid or wrong, it is your job to correct me, because that is not what my background is. So, but yes, you have favorite lectures you like to give and other topics that are like, ugh, this is one of my favorites. We get to finally start talking about the models that you came here to learn, building into something new. And we can talk about how they build on what you have already learned and what the new parts are, as well as some new type of notation. So that's always exciting, to be able to crack the code that other people use in their written work. So are we ready to go? Are you ready? Lecture 4? Okay. Then let's do this. So reminding you of the big picture here. What we're trying to do in modeling longitudinal data, we have two sets of things to figure out. What goes in the model for the means with respect to time, what goes in the model for the variance. What we did last week, the last couple of lectures, lecture 3 and chapter 4 in the book, was focus on the right side here, with in-person fluctuation. When you have data in which there's no systematic trends related to change over time, time probably doesn't have much to do in the model for the means. So that's why I have on the top here with in-person fluctuation, you may not need anything. And in the examples that we looked at, there were no fixed effects related to time because people didn't change. In the model for the variance, what we were trying to do is describe the pattern. So are all the variances the same over time or not? What type of pattern of covariance do you have? Is it constant? Does it decline over time? Are occasions that are closer together in time more related? We're identifying different types of patterns that would be consistent in replicating what the pattern is in the data. So we're still seeking the same ends. We're still trying to describe the pattern of variance and covariance over time, but now we're going to be doing it in this kind of data on the left here, with in-person change. This type of data has different patterns to it. So we'll have a different set of choices, but the end goal is the same. Try to come up with a pattern that best matches the data. That way the standard errors for the fixed effects that we care about are as accurate as we can make them. So in terms of the model for the means, so far you know two options at your disposal for modeling mean change over time. And just as we talked about a continuum from parsimony to complexity for the variance model, we have the same thing on the mean side now, because time will be relevant. So you know one, over here on the left, empty model. There's no effect of time, no effect of anything. Empty means no predictors whatsoever. Every type of longitudinal data can have an empty model fit to it, and that's the first thing that we typically do to get an interclass correlation, find out how much of our variation is actually longitudinal. The other side, the term saturated means, this is ANOVA. This is the idea that time is a discrete variable. Rather than trying to model a functional form of change, we just let the means be whatever they want to be. So there are as many parameters as there are means, as there are occasions. So 5 parameters, if I have 5 occasions, perfectly reproduce the 5 means. You can only do this if you have balanced data. If people round themselves neatly into time 1, time 2, time 3. If you have a data set where it's unbalanced and everybody has their own set of times, this model may not even be possible to estimate, because it's going to try to come up with a predicted mean for every possible unique value of time. So time 2.61, time 3.75, all of them, and it may blow up. So this model on the right here is usefully for descriptive purposes. It's the answer key. If I have 5 occasions, I have 5 means. I can plot those 5 means and get a sense of what kind of trajectory of a line I could fit through those 5 means. If I don't have balanced data, I would still want to get something like this. I may round time into convenient intervals just to get a sense of what the pattern is that I'm going to try to model. What we would then do is something in between. So we're trying to find a model that will approximate the trajectory through the means. And depending on the type of context that you're in, the type of change that you have, there are lots of different options available. We'll start with the simplest and we'll proceed to things that are much more complicated to fit with few occasion data where you need lots more data. Polynomials is most common. Piecewise models are known as linear splines. Is that a term you've heard before? Discontinuity, yeah. Those are really good for intervention kinds of designs. So like where you have a period where you do one thing to your people and then you switch up your protocol and you do something else, and you want to know if they change differently under each set of protocols, that lends itself very nicely to these sorts of piecewise designs. We have all sorts of options, but the end goal is to try to find something that predicts the pattern of the means as well as the means themselves, but more parsimoniously. So that's what we're doing on one side. On the other side, it's the same slide that you saw before, now with a different part highlighted. We still have the same endpoints in terms of fitting the model for the variance. We have compound symmetry, which is random intercept only, as the simplest model we would entertain for longitudinal data. And we have unstructured as the most complicated. Every variance and covariance gets to be whatever it wants. There is no structure, it's unstructured. This is the MANOVA approach to repeated measures. It's only possible in balanced data. This is the answer key, the H1 or saturated model in structural equation modeling terms. So we are trying to come up with a pattern that fits as well as unstructured but uses fewer parameters. And in models of change, the way that we're going to do that is by introducing random effects in addition to the random intercept. So terminology, random effect is the biggest term. A special type of random effect is a random intercept. You know that one already. Now we're going to have random slopes as well. So the set of intercepts and slopes you can think of as random effects in a general sense. And the good news is that they can predict patterns even for data that are unbalanced. So whereas unstructured is not possible to estimate when everybody has their own set of times, random effects models are. And so that makes them super convenient for real world types of problems. Okay, with me so far? Okay, so, yeah, please.
In SEM, we have also another term as just identified model. Is it the same as the saturated most of the time, or?
Just identified is a term meaning that the model you've chosen uses as many parameters as it possibly could. By definition, this is a just identified model because you have all of these variances and covariances going in and you're estimating them. There are other ways of making a just identified model that would be different than this, but just identified just means that there's nothing left on the table and it should fit perfectly.
So, is it the same as the saturated, or?
Okay, let me give you an example.
Okay.
So let's say that instead of 4 occasions here, I only have 3. Okay. I'll stick with my current example. If I have 3, and this is like a measurement model where these are items, what happens if I fit a factor model to 3 items? What kind of fit is that? If I estimate all the loadings, all the residual variances, and all the intercepts separately. That's just identified. So, in other words, that's a factor model. That's not an unstructured matrix. But it's just identified, meaning it fits equivalently to if I just let the 3 variances be what they want and the 3 covariances be what they want. So there are 2 different models in terms of the parameters that are being estimated, but because we've spent as many parameters as we have pieces of data that we started with, it's just identified. Does that help?
Yeah.
Okay, we'll see more examples of that are relevant to this class today. Because yeah, you can end up with random effects models that spend as many parameters as unstructured, in which case they fit the same, but they're not the same model, they just fit equivalently. Other questions? Okay, so two sets of patterns. Mean side, what's happening on average? Variance side, what's the pattern of variance and covariance that these trajectories are creating? So we're going to do a little bit new notation here to get us ready to add some more random effects to our model. You remember this picture, right? This is our starting point for all longitudinal analysis. Empty model with respect to the means, no fixed effects, no time, no nothing. Variance model, we start with random intercept variance, that's level 2, between persons. Intercept means mean differences specifically, so each person gets their own mean. We don't know why each person needs a different mean. So that's unexplained variation, but we know it's person level variation. We know that it's cross-sectional, it's mean differences. At level 1 then, residual variance, that's E variance, individual variation within a person around their mean, that's the longitudinal part. And so we always start with this model so that we can figure out the relative contribution of between person random intercept variance at level 2 relative to within person residual variance at level 1. Here is a new way of writing that idea. This is your very first multi-level model. So subscripts, super important. Color coding, me trying to help you get the patterns of these things down. So if I had an empty model that was a general linear model up here on the top left, y sub I. So if I fit a regression, each person has one outcome, a cross-sectional model. That's why it's y for each individual. Because each person has one y, they have one e. So the model for the variance in a regression model has one term in it. This e, which represents the idea that each person has an E, and what we care about is the variance across people of these E's. We call it residual variance. The model for the means in this case is empty. If we have no idea, we have no information about anybody, our best guess for their Y is going to be what? Grand mean, right? So that's what this is. That's our jumping off point. So this model would simply spit back at us all of the variance in Y. Variance defined is the difference between each observation and the mean squared divided by n minus number of fixed effects. So this would just recreate the sample variance for us. It's the worst we could ever do. In a longitudinal context, we want to start from the same place, the worst we could ever do, but it's a slightly different place because we do know something about each person. We know from which person each observation came. So rather than starting out with a naive guess that's just the grand mean for the sample, we want to start out with a naive guess that's each person's mean. So we have what is called now our level 1 model within persons. YTI. In my notation, T is time, I is individual. No one's going to tell you this outright, but I will. You get to pick whatever letters you want. There is no law that says it has to be IJK or someone's going to yell at you. It kills me when I see things like IJ, because it's like I is time and J is what? I don't know. So I always pick letters that to me make it easier to keep track of my levels. So I could go TP. Sometimes I do that if it's person. Sometimes I go TS for subject, depending on what else is in the model. It gets tricky when you have like subjects in schools because then you have 2 S's and you get creative. But I stick with TI. Time with an individual. Because each person has a Y per time, they have an E per time. So in terms of variables that go in this level 1 within person model, all of them get a TI because they are per time per person. Beta 0 now gets an I. So beta 0 is going to become each person's intercept. Now note that beta 0 here is not red like it was up here. So in my notation here, model for the means is red, model for the variance is blue. Beta 0 is black because beta 0I is not a thing. It is a placeholder. It is not an estimated parameter. It's a placeholder that we then define at level 2. Beta 0I is the idea that each person needs their own mean. How do they get it? It's a combination of fixed plus random. So our new fixed intercept is gamma 0, 0. This Y-looking thing is a gamma. In some fonts it looks like a V, some fonts it looks like a Y, but it's gamma. Y at 0, 0 is because it's the starting point for all fixed effects in the model. The pattern of subscripts will make more sense once there's more of them to contend with, but just briefly for now, the first term in the subscript goes with which term in level 1 it's referring to. So because this gamma 0, 0 is predicting beta 0, it starts with 0. The second term refers to the order of prediction within the level 2 equation. So this is the intercept, it's the starting point of this equation. If I had other terms in here, predicting beta 0, it would be O1, O2, O3, O4. If I had other betas up here, like if I added a beta 1, then the subscripts down here would go 1, 0, 1, 1, 1, 2, 1, 3. So think of it as like a grid, where the first term indexes what beta you're talking about at level 1. The second term is the order within that level 2 equation that further defines the level 1 term. So beta 0i is not a thing. And if I wrote it out as one equation instead of two, it would look like the bottom right corner there, the composite equation. So how does each person get their own intercept? The fixed intercept, gamma 0, 0, that's the grand mean for the sample. And then the random intercept for person I. So you can think of this as one distribution where gamma 0, 0 is the mean, and then U0 is how far off from the mean yours is. So if my mean is higher than everyone else's, my U0 is positive. It has a mean of 0 because its mean is right here. It's gamma 0, 0. So fixed in general means everybody gets the same. It's the constant part that's equally applied to everyone's prediction. Random means everybody gets their own. U0i is just for me. You get one, you get one, you get one. Everybody gets one. And just like up here, this E stands for the idea that we don't really care about what the E's are per se, but we care about their variability. The same is true here. I don't need to know what your U0 is. It will not show up on the output because it's not an actual parameter. It's the variance across people that's the parameter. Said differently, U0 is a factor score. We don't need to know what it is. It's an idea that each person needs their own intercept deviation and that we care what the total variance of those deviations is across people. So it's easier to see the three parameters of the model if you look at the composite equation. There's one fixed effect, which is the fixed intercept gamma 0, 0, grand mean. There's one random effect, which is the random intercept variance. And U0 is for one person. We care about the variance of the U0s across people as the model parameter. And then there's one E per occasion per person that then is the difference between each person's mean and where you are at that particular occasion. And we assume that E has one variance. E variance is supposed to be constant across people and constant across time according to this model. And it also has no covariance. So by definition, any term about variability that's at a different level has no covariance. They're orthogonal. So we add up the U0 variance plus the E variance and we get to total. We're allowed to sum them because they're orthogonal, they're uncorrelated. That will not be true once we add other terms at each level for which we also have to estimate a covariance. Okay. Questions? All right. So that's one example model with respect to the model for the means, empty means. What would the other one look like? Here's what a saturated means model would look like. So you don't typically do this, but if I were to write out a repeated measures ANOVA, the univariate version, as a regression model, this is what it would look like. So if I have 4 occasions, for instance, in SAS and SPSS, for example, the last occasion would be the reference, when you let it do the coding for you, when you denote the variable as a categorical predictor. So that's the class statement in SAS, that's I dot in Stata, that's by in SPSS, and that is a factor in R. So these would be dummy codes for the difference between time 1 and the reference time 4. The difference between time 2 and the reference time 4, time 3 and the reference time 4, where beta 0 I would be time 4. So at this point, how many betas do you see in my level 1 equation? 4. Guess how many betas show up in my level 2 model? 4. Not a coincidence. Each one of these is a placeholder for how each person is going to get their own version of the effect. So beta 0 I is going to be, according to this model, the intercept, which is the expected outcome when all the predictors are 0. Given my coding, that's time 4. So gamma 0, 0 would be the expected mean at time 4. U0I is how far off from that mean I am relative to everybody else. It's a random intercept. Beta 1, 2, and 3 only have fixed effects. So gamma 1O is 1O because we're predicting beta 1, and this is the first entry in the line predicting beta 1, so we start counting at 0. Likewise, 2O is for beta 2, 3O is for beta 3. The fact that these do not have any blue terms here, that these are fixed effects only, means this model predicts that everybody changes the same. So people get their own starting point in the sense of their own mean at time 4, but then everything is parallel from there. The model is agnostic as to what the pattern of change is. It could be linear, in which case these dummy codes would be approximately the same size. It could be quadratic-y, it could be any kind of weirdness, but it's parallel, whatever it is. That's what the model says. That the only way that people differ from each other is in their intercept, and that's it. In other words, the dependency introduced by longitudinal data is constant dependency over time. Here's what the model is saying then about the pattern of that dependency. You've seen this before. We looked at this last class, and we'll see it again throughout the semester here. Here's V. So remember our vocabulary? Level 2 random effects variances are going to live in a place called G. Level 1 residual variances and covariances are going to live in a place called R. So G holds your level 2 variability terms. R holds your level 1 variability terms. That means G is between or within. Between. R is within. Wrapped around G then is this Z matrix, which has as many occasions for this person. So this person has 4 occasions. And because all we have right now is a random intercept, that's why it's a column of 1s. So we're going to start adding to that this week. So when we have G plus R, and I know you can't see it on the home audience, but I'm making air quotes around plus, because I know you can't add them. That's what the wraparound thing is for, to make it work. G plus R, V gives you the total composite pattern. So the total variation at each occasion is part because of level 2, part because of level 1. It's the same across occasions, and the only reason for covariance across occasions is random intercept variance. People differ from each other in one way, and that's the only reason occasions from the same people are correlated. So regardless of whether you have a means model that differentiates time, change over time, or not, like an empty model, The variance model is the same. The variance model says something very specific. People differ from each other in one way, in intercept, and that's it. Okay, with me so far? Okay, so that seems unrealistic. So let's add to the model. In asking ourselves, how do we model change over time? How do we put time into the model? We have to answer two questions. Number one, is there an effective time on average? If I drew a line through those sample means, would the line be something other than flat? If so, then we need some kind of fixed effective time, where fixed is the part that everybody gets. The extra part, the part that ANOVA cannot get you, repeated measures ANOVA cannot get you, the new part, the reason you're here, dare I say, is an additional supplementary question. Does the effective time vary across people? Do people need their own version of whatever that slope is? If so, then we have a random effective time, 2. And you can have either, both, neither in these patterns here. So I have the 4 possible patterns that you might see in terms of fixed versus random. Intercept is random in every figure, so we're just focusing on the slopes, okay? So x-axis is time, y-axis is your outcome. Heavy black line in these figures is the sample means, and the thinner lines are best fit trajectories through individual people's data. So if you have a picture like this, I would say there is neither a fixed effective time nor a random effect. There is no fixed effect because this flat line through the means says there's no change on average. There's no random slope, no random effective time, because everybody, no changes the same. That flat line does a good enough job for each individual, so there's no random effect. If we have little dots around these lines, then we would still be in business, because we don't have to have change to have it be longitudinal data. So this is a common misconception. Folks ask, like, well, do you even have longitudinal data if you don't have a fixed or random effective time? Depends. What do you need to say that you have longitudinal data? Different occasions. That is a prerequisite in front of the thing that I'm going for. Put ICC in your answer somewhere. How do we know we have longitudinal data? Assuming we've sampled people multiple times, how do we know that we have longitudinal information in our data? We have a small ICC, something less than 1. So it is possible. You could have this type of pattern and have an ICC of 0.5. It means that you have within-person variation. You don't have within-person change. 2 different things. Let me go back to the first picture here. It's the difference between these 2 pictures. If you have neither a fixed effective time nor a random effective time, that's the picture on the right. There's no change on average and people no change the same, but there is still variation over time. It's just not systematic with respect to the x-axis here that's time. It might be systematic with respect to other things that you've measured over time. So we're focusing on the left picture here.
I got one question. So in the right side, you say that those patterns indicate no longitudinal?
No, it's longitudinal.
It's longitudinal.
It's, I would call it, you have fluctuation, not change.
So if we got data like that, we still need to do longitudinal analysis, right?
So long as your ICC is under 1. Yep. I'm just saying this is the way that that can happen. People are changing relative to their own mean, but they're not changing as a function of time. So think of this as characterizing like an observational study, where you ask people to answer questions about themselves every day. You're not trying to fix them, you're not trying to hurt them, you're just asking them how it's going. So it doesn't matter to them if it's day 1 or day 7. What matters is what's going on in their lives. versus a design like on the left, there the y-axis is something where you've deliberately chosen those occasions because you expect people to show systematic change across them. They're learning how to read, or they're aging and they're showing deterioration, or you're trying a new drug and you want them to get better. Those are different kinds of designs for different purposes. But so long as you have an ICC under 1, so long as you have some kind of level 1 variation, then you have some information over time to work with. It doesn't have to be time systematic. Go back here. Where are we? Here we are. Okay. So that's the first one here. Next one. Yes, we have a fixed effective time because on average, people are increasing. But that rate of average increase appears to hold for everybody, so there's no random effective time. People don't need their own. These are the only 2 situations in which the univariate approach to repeated measures ANOVA is going to be valid. These are the only 2 situations on this page where the variance stays constant across time. The lines are parallel. There's no difference in the effective time across people. Now, this is the most interesting situation here. Let's say that you do a longitudinal study for your dissertation. I wouldn't recommend it, but some people do. And you spend a whole year of your life carefully collecting data, and you run your repeated measures ANOVA at the end of it, and you find out you have no main effective time. Wah, wah. That's the sad noise. Wah, wah. So you might go home, get yourself a bucket of ice cream or a bottle of wine, or maybe both, depending on your preference. And you might be really, really sad, but then if you came to see me, I'd be like, no, wait, let's make some pictures. And if you got a picture that looks like this, we're back in business. Because even though there's no fixed effective time, on average, there's no change, it's because people are changing differently. And they can actually cancel each other out. And so if you were doing a treatment study, now all of a sudden it got a lot more interesting. Because you did make some people better, but hey, you made some people worse. Shit, now what? Don't you want to know what was it about some of these people that reacted so badly to what you were doing? That's an interesting story. So just because there's no fixed effective time does not preclude having a random effect. People can still need their own, even if on average there's no change. And then you can have both. On average, people change, and people show differences in the extent of that change. So these bottom 2 pictures then, the intercept variability, the spread of differences in the people means has to change over time. People are spreading themselves out. And so we have to have a model that allows the variance to change over time. And even though you can't tell from these pictures if the variance is changing over time, odds are good the correlation is changing over time too. Occasions that are closer together are going to be more related. So by adding the possibility of random effects of time, we are allowing variance and covariance to change over time. Yep.
Does that require us to have at least 3 occasions to have random effects of time?
Yes, it does. Yep, because either if you have only 2 occasions and you give each person their own line, how well is that line going to fit?
Perfect.
Perfect. So either people need their own lines and there's no residual variability whatsoever, or you've got residual and everybody's lines are the same. You can't differentiate between those 2 situations with 2. You got to have 3. And what if only some people have 2 and some people have 3? Give it a shot. If, as it turns out, just like everything else, whether or not we need a random effect of time is going to be a likelihood ratio test. So you'll have an empirical answer as to whether or not you have enough signal to be able to detect it. So the empty model that we started with, that has just a fixed intercept, U0 variance at level 2, and E variance at level 1, that would make a prediction like the top left here. So now let's add things to the model that would allow these other possibilities to exist as well. So first, we're adding fixed effect. Yeah. So my level 1 model has picked up a new term. I'm calling it time. We're working with just linear right now because we can start with linear and the concepts are the same once we get to more complicated stuff, but let's just pretend it's linear. If you only have 3 or 4 occasions, that's probably a reasonable thing to do. So we still have an individual intercept as a placeholder, beta 0I. We've picked up another placeholder, beta 1I. This is going to be how each person gets their own linear effective time. Note that time is the predictor variable, and it gets a TI because time is measured per time and per person. So the latter is necessary to denote that each person could have their own set of times. It doesn't have to be time 1, 2, 3, 4. It could be time 0.9, 2.6, 10.2, and whatever. Because we have 2 betas now at level 1, we have 2 level 2 equations, 1 for each. The beta 0I intercept equation looks exactly the same. We have a fixed intercept, gamma 0, 0, plus the random intercept, how far off U0, how far off you are from the fixed intercept. The only difference is now what this means. Previously, if we had no predictors in the model, the fixed intercept is the grand mean. Now, fixed intercept is the expected outcome when all the predictors are 0, which is time 0. So this entails that you've already thought about what time 0 should be, and you've coded your time variable accordingly. There is no wrong answer for what time 0 could be, but there's plenty of weird ones. So let me give you an example. In cognitive aging, it's not uncommon to have samples of older adults starting at maybe age 60 up to however old you can get them. What happens if I put age in the model here, and I just put it in straight up? My fixed intercept would be the expected outcome for what kind of person? A newborn. Is it possible mathematically, here's my math expert, is it possible mathematically to develop a prediction for a newborn from people who are 60 and older? The line keeps going, right?
Yes.
Mathematically, but does that make any sense?
No.
No. And where it can cause problems is when this random intercept becomes conditional on time 0, 2. We're not there yet, but that's the next step. So in addition to trying to figure out what the average outcome is for a newborn, the model would be trying to estimate the variability across newborns as given by older adults. And it may actually just blow up because it's not going to be able to do it. So time 0 just needs to be somewhere within the scale of your data. The first occasion is a fine place to put it. That's probably the most common. In certain situations, you might want to put it at the end occasion if you're really interested in what happens to people as they get further along in a process. If there's a critical event that happens partway through, maybe that could be your time 0. It's up to you. There's no wrong answer, but there's plenty of weird ones. Yeah.
Can we use the centering method?
The centering method?
Yeah, for the time.
You want to center it at mean time?
Yeah.
Sure you can. No, that's fine, but if you have time 1, 2, 3, 4, what's the mean of 1, 2, 3, 4? Like 2.5, I think? That sound about right? Do you have a time 2.5?
No, just 2 or 3. Interrupt.
Yeah, it's between occasions is where I'm going. So then your reference point is it's an occasion you didn't actually observe. There's nothing wrong with that because your model extrapolates, but it's a little weird. So, but yeah, that would be fine too. So fixed intercept, expected outcome at time 0. Random intercept, how far off you are from that. And beta 1i is how each person gets their own linear slope for time in this model, and it's fixed only so far. Everybody changes the same according to this model. That's how we get this top right picture. That's what this model says. If time has a positive coefficient for the fixed effect. So if we wanted to write it as one composite equation rather than level 2 and level 1 split out, it would look like this on the bottom, where fixed intercept plus random intercept is beta 0, and beta 1 is just gamma 1 up. When you write these things for people, sometimes it's more convenient just to lay it out as one equation, and sometimes it's more convenient to do it this way. It's a choice. There's not a right or a wrong, so long as you're internally consistent with your notation. See, I warned you that I didn't have a math. I can't do simple division on the fly in front of you and have it be accurate. The good news is that math is not required. It's all logic, because SAS will do math faster and better than any of you.
I believe so.
Yes. Yeah, have you guys seen the movie Hidden Figures? A few of you? I read the book, and the movie took some liberties in terms of making the story much more interesting. But I love the fact that, it's a great movie, by the way. It's a true story about when we were trying to get to the moon. NASA hired a whole bunch of what they called computers. And a computer was a person who had enough math and engineering training to do calculus and try to figure out angles, probably some geometry too, right? Yes, lots of really hard, fancy math where it takes up like the whole blackboard to write an equation. And they did it all by hand because they literally didn't have computers. And so they were computers. And then they got a giant new computer, and it took up like probably the size of this room. And turns out it didn't work right. And some of the calculations disagreed with the hand calculations. And there's this one really pivotal moment in the movie where the guy's like, I want her to do it, one of the main characters who actually put them on the moon, because he trusted her computing over the computer. That doesn't happen anymore, okay? I don't care how good at math you are. SAS will do it better and faster. So, and they had to learn Fortran to be able to program it, and that's a useful thing too. So anyway, it's a good show. I highly recommend it. But anywho, I don't do math. I tell SAS to do the math. I just stand up here and point like Vanna White. Like this. Okay. Anywho, so fixed effective time. You with me? Okay. So, hello.
We're just doing a tour. Sorry to interrupt.
Okay, yeah, well, this is a lovely classroom with laptops. So fixed effects. Fixed effects are in the model for the means, right? That means we actually are going to explain variance for the very first time. How much variability do we explain by putting in this fixed effective time? Now that's a tricky question, because right away I have to say, well, which variability? How many kinds of variability do we currently have in the model? 2. So here what's going to happen is non-intuitive, and I want you to be prepared for it. Lest you think that SAS screwed up and got the math wrong. It didn't. So one of the ways that we will talk about effect size to go along with our significance test for fixed effects is something called pseudo R-square. That is a term. That is not me being funny. That's like literally what it's called. You can use that term in your papers. It's the idea of calculating the proportion reduction in each distinct source of variability in your model. So it's analogous to an R-square that you're used to in regression, but there's going to be as many of them as you have variance components. So we have 2. So the formula for it, generically for pseudo R-square, is whatever the variance was in the simpler model minus what it is now after adding your fixed effects divided by what it was. So simpler model minus the current model over simpler model gives you the proportion reduction. In this case, figuring out what should happen to the variances is as simple as figuring out what line the predictor's in. Time is in the level 1 model, therefore the variance that it should explain is a level 1 variance. And that's going to hold true anytime you're looking at these multi-level equations where things are broken down, where there's an error term as part of each one. Whatever fixed effect you put in your model explains the error term in its equation. Because we put time here, it should explain E. Now think of it this way. E variance is within persons, right? E variance is over time variance. Time is a time level piece of information. So of course it should explain over time variance. In contrast, U0 variance is person variance, right? It's mean differences between people. So what kind of variability would explain differences between people? People things. Things that are constant over time. People characteristics that you've either measured once or it's the mean across occasions, for instance, for things you've measured more than one times. So E variance should go down. So we can calculate what happens to it in instances in which time is not just within persons but also between persons. This is an advanced topic. It's chapter 10, but I'll foreshadow it now. That can happen in what's known as an accelerated longitudinal design. So this is common in school settings, like you might go into an elementary school, grab first, second, and third graders, and measure them like once a semester until they age out. So you start with the first, second, and third graders, and then you measure them when they're in 2, 3, 4, and then 3, 4, 5, like that. In that case, time, if you just put in grade, there's two distinct sources of variability in grade. There's the one that you wanted to be there, the change over time because you're measuring them repeatedly, and there's the accidental one because you started off with first, second, third graders. Think of it as a cohort. So the grade that you started in is a between-person source of difference. The grade that you aged into as the study went on is a within-person source of difference. And those could be two different effects in the model. So if you have a variable like that, where time is not just within persons, but also varies between people because people are at different points in time when they start, then it could also explain U0 variance too. But in most simple examples where everybody is at the same point when the study begins, it should explain E variance. What makes this confusing is that once you explain E variance, your U0 variance is going to increase. It's going to make it look like your model got worse instead of better. But it's completely an artifact of how the U0 variance is estimated, and so I want you to be prepared for it so that you can explain it if you need to. So the U0 variance that shows up on your output, I've been describing that as level 2 between person mean differences, right? If you took your data set and you calculated the mean across occasions from a person, and you calculated the variance of those person means, just ran descriptives, that number would be bigger than what SAS gives you for the between person variance. The observed variance is bigger. That's because SAS, or any likelihood algorithm, by the way, it's not just SAS, they all do this, it's trying to figure out how much of that between person observed variance is actually just sort of noise. So for instance, if I took this group of people and I randomly assigned you into, let's say, 3 groups, and I measured the mean height of each group, would those means be identical? No. They shouldn't be systematically different because of the random assignment, but there's going to be a little bit of difference, right? Just because of the people who happen to be in a group. So SAS is trying to figure that same distinction out. Okay, how much of this is real mean differences versus just like a little bit of expected noise? And the way that it isolates what it thinks is expected noise is by this term right here, residual variance divided by the level 1 sample size. So it thinks that its observed between person mean differences is part sort of true differences plus a little bit of noise because of the observations within each person. So when it estimates between person random intercept variance, it's trying to back correct and get you the true one. And so it takes the observed and subtracts off this correction factor. So here's some numbers just to show you an example of how this works. You'll get a handout here. This is example 5, and this is also the first part of chapter 5. So let's say that I calculated each person's mean across 4 occasions. I took the variance of those person means and I got this number right here, 4.65. And let's say that I ran an empty model and I ended up with residual variance of 7.06 for my 4 occasions. It's going to take that 4.65, that is the observed between person mean difference, try to correct it, downweight it for how much is noise by taking the residual variance of 7.06, that's a typo here, divided by 4, and it's going to come up with this new number. So on your output, it's going to be 2.88. That's what it thinks is the true between person variance. Whereas the true level 1 residual variance within persons is 7. If I put in a fixed linear time slope, let's say there's a strong trend in the data, and I find that my new estimate of level 1 residual variance goes from 7.06 down to 2.17. So now what shows up in my output is a new level 1 after controlling for time variance of 2.17. So if I take 7.06 minus 2.17 divided by 7.06, I get an R square of about 70%, 0.7. So 70% of what was level 1 variance is because there's average change. Time has explained 70% of the within person variance. But the level 2 variance should be untouched. If everybody has the same set of occasions, time doesn't vary between persons, level 2 person mean differences should still be the same. So it's going to start with that same number, that 4.65, but now it's going to subtract off a lower amount of what it thinks is due to noise, which is going to end up with a higher value for true between person mean differences than what we had before. So Ori, in the example you showed me, you had you fit models where you were looking at an empty model to see how much variance was across students and schools, right? Remember this? I remember this. Because one of the rows was empty. There was no variance across schools, I think it was. It was cross-classified, that's right, because students and schools were crossed at level 2. And and it had 0. So the lowest value that a variance can be is 0. And so that may be what you get back on your output, is a 0 where the estimate is and a bunch of dots where like the standard error and other stuff should be. Dot is not a number. It means I gave up. My best guess is 0, I have no idea. I think it's 0, and I can't give you a precision because I have no idea. So if you were to then put time in your model, guess what happens to that 0? It's going to go up because of this. Because there'll be less residual variance in the correction, and so it's going to come back. So this matters for 2 reasons. Number 1, when you put time in your model and explain level 1 variance, or more generally, when you put any level 1 predictor in and explain level 1 variance, your level 2 variance is going to go up. Doesn't mean the model got worse, doesn't mean you did something wrong. It is a consequence of how it is correcting true versus observed for level 2. The other reason this is important is because some people would tell you, well, do you even need to do a multi-level model in the first place? What if you fit a multi-level model and you don't have any level 2 variance? What if your ICC is 0? It's all within, there's no between. Does that mean that you can just go back to regression? What do you think? It seems reasonable, but the problem is that it's not going to stay 0. Once you explain level 1 variance, that 0 is going to go back up to something positive. So you can end up with a higher amount of dependency after you've put in your predictors than you started with. And that happened in our example 3A. The intraclass correlation in the empty model was like 0.3. The intraclass correlation after putting in the predictors was 0.8. So of the variance that's left, 80% of it was between. So this phenomenon means that there really is no situation in which you can ignore a multi-level data structure. Only if it were 0 and no matter what else you did it stay 0, would I feel okay with not having that level in the model if it's part of your sample. It will come back. The variance will come back. So this R square here of 70%. So some of you were in Jonathan's class, right? He had an R square in his example of like 0.95 or something, and he was laughing because that never happens in life. Now these are simulated data, but would you get super duper excited about an R square of 0.7? Right? Now, if I wrote this up as if this were a regression and I said my model has an R square of 0.7. Not cool. That's cheating. Why is it cheating? Because this is a pseudo R square, not an R square. So if I look at the numbers here, I'm going to need someone to do the math for me here. If the random intercept variance is 2.88 and the level 1 residual variance is 706, what's the interclass correlation? 2.88 divided by 2.88 plus 706. What is it?
Around point.
It's about the same. I don't know, it's in the past.
0.3?
Yes, 0.3.
0.3-ish. Okay, I can work with 0.3-ish. So if you think about this, 30% between, 70% within. So what this R square means is of the 70% that was within to start with, my fixed effective time captured 69% of that 70%. What is 69% of 70%?
Could you 15, but 50.
50%. So this is a partition of a partition. So the variance that was eligible to be predicted from time as a fixed effect is the level 1 within variance. Relative to the original total, if I have an ICC of 0.3-ish, you guys just said, that means the within part is 0.7-ish. So this pseudo R square means that the fixed effective time explained 69% of the 70% that was related to time in the first place, that was within persons. So on the whole, if I wrap that all back together again and just want to talk about the data, my R square for the whole data put back together again across the piles is roughly 50%, not 70. And so you will see instances like this, particularly in clustered samples, you have to keep this in mind. So when you have things like students nested in a classroom or a school, most of the time the ICC will be like 5% to 10%. I think 15 is about the highest you'll see in real data. And I have an example that I do that's clustered MLM where my differences between schools due to free and reduced lunch explained 70% in a real data set of the level 2 variance. But that's 70% of the 10%, right, that was level 2. So these pseudo R squares always have to be placed in context. And the easiest way to do that is to make sure that you don't say variance explained, but you're more specific. Like I would say, it is 69% of the residual variance at level 1. That's accurate. It's not 69% of the variance, period.
So I got a question.
Yeah.
So in this scenario, it looks like so in this example, we used time as the covariate.
Yes.
But in more general case, it looks like the covariates we pick, like influence the partition of the between person variation and within person variation.
Yes.
So it's not like their proportion is constant.
Correct.
So how do we justify like different covariates? Because it's even in linear regression, it's hard to pick covariates.
So in these models, in longitudinal data, time has a special role, and you always have to start with that, because the piles of variance that are going to eventually be eligible to be explained by other covariates are going to depend on what your model for time is. So for instance, let me go back to this right here. Let's say that I did all of my testing and I decided this was the best model with respect to time. That means that in terms of sources of variability that my covariates have to explain, I've got E, which is remaining within person variation that's not due to time, and I've got U0, which is between person mean differences. There's only 2. Instead, let me flip ahead here just a second. What if I pick up this? This is going to be my random linear time model, where I pick up a U1 that does the same thing as U0. So in this model, gamma 1O is the fixed slope, the part that everybody gets. U1 is how far off my slope is from the fixed slope. If I decide this is my best model, now when thinking about covariates, I've got 3 different types of variability that they can explain. I've got, why are you off your line today? Like, what is it about the within person, what's happening today that's not about time? I've got, why did you start out differently than everybody else? Person mean differences. And now I would also have, why did you change differently than everybody else? So covariates would have 3 distinct roles that they could fill. Any level 2 predictor could tackle these 2. Any level 1 predictor could tackle that one. So time has a special role, and then it dictates what else is going to happen. In terms of what covariates to pick, they should be the ones that either someone is going to yell at you if you don't put it in, because you have to control for it. Every field has at least one of those. And then whatever is necessary to answer your questions. I can't give you any more specific advice than that, because it totally depends on the context. But answering questions should be the job of the model. So. Let me go back. There we go. So, because time has a fixed effect that is a level 1 term, it explains E variance. That's where we were at. Putting that into context requires an understanding of how much E variance there was in the first place that was eligible. Okay. Other questions? Okay, we did that. So this is, someone showed this to me after class. Who was that? Someone did this derivation. Was that you? Showed this to me? Yeah. So this is my way of showing what does it mean in terms of the variance model to only have U0 and E? It means that people differ from each other in one way. So if I write out this model, this is where we're at right now. My composite equation will make this the easiest to work with. This equation tells me how the model predicts the variability at each occasion and the covariability between any 2 occasions. And in this case, it's pretty straightforward. You can drop out any constants that are just sitting there. So we end up with just the variance due to U0 plus the variance due to the residual. And so that's my total variance at any occasion. Doesn't matter what occasion it is, it's going to be U, part E. That's compound symmetry. Same thing with the covariance. If I write out the predicted covariance between any two occasions, A and B, drop out the constants, the only term that shows up is U0. Because the E's are supposed to be unrelated, and the U's and the E's are unrelated, so everything else cancels. So the model says that. So that's how we get back to the same compound symmetry, constant variance, and covariance structure. If you read it in a stats book, it's going to look like this. So this is what the model looks like in matrix form to predict one person's set of outcomes. So capital Y here is a matrix that has only the data for one person, and actually it's just one column. X is a matrix that holds the values of the predictors that have fixed effects for that person. So because we have a fixed intercept, that's the column of ones. The next column over would hold their values for time. So this would be a simple case where it's just time 0, 1, 2, 3. Gamma, in my notation, this would be called a design matrix, by the way, for those of you who've had other classes. Gamma is a matrix of fixed effects. And then over here, Z and U. Z is a matrix of the predictor values that have random effects also. So in this case, we have a random intercept, but we don't yet have a random slope, and that's why the time column's not here yet. Because we only have one random effect, we only need one U. And then we have our matrix of E's, 4 per person if we have 4 of occasions. And you can fill in the values and work out the math. And then we get back to this picture, which you've now seen a few times, of how it builds the total composite V matrix. Random intercept variance in every location, residual variance on the diagonal. So the cool part then is coming next. What happens to this type of prediction once we have random slopes? And what's going to happen is that every person gets their very own customized V matrix based on whatever occasions that they have. It's super cool. But that's coming next. So summaries thus far, wrapping up so we can get going. So far we've seen 3 different alternatives for the means model with respect to time. Empty, nothing in it. Saturated, time is treated as categorical, as many parameters as you have occasions. And we have fixed linear time so far. All of these choices have had the same model for the variance. That's a random intercept only. That means there's only one source of differences between people at level 2. It implies constant dependency and constant variance and covariance. So then what's next is changing up the model for the variance. It should be more flexible and better suited for data that show individual differences in change. So, there we are. Questions? All right, then we will pick this up next time. Today's Tuesday, so next time will be Thursday. Homework is due tonight. Let me know if you have any questions. Office hours start now. And there's a quiz to do for next Thursday too, I believe, is it? Let me make sure that I'm telling you the right information. Yep, there's a quiz that you can work on that we'll go over on Thursday as well. So, see you then.